All right, what we're going to talk about today is what are sequences, okay? And sequences, if you're familiar, are is a pattern of numbers. Pattern of numbers. Some could also say a set of numbers. A set of numbers. Now these numbers generally come in a pattern. And that is generally what we try to do when we talk about sequences. We try to figure out the pattern of these number sets. So for example, if I was talking about an infinite sequence means it goes on forever. Okay? So if we have an infinite sequence, okay, let's just say that we had a number set, something really simple, 2, 4, 6, and 8. Who do we appreciate? Sequences, sequences, sequences. All right? So we have this infinite set of numbers, this sequence right here. So we have 2, 4, 6, and 8. Well, in a sequence, you can see that since we have a set of numbers, we can define these different numbers as terms. Okay? Sequences have terms. Okay? Have terms. So in this first one, we would say term 1, and we would go a sub 1. Okay? A sub 1. Now, when we look at a sub 1, we can see that it's going to be equal to 2. All right? A sub 2, our second term, is going to be 4. Our third term is going to equal 6. And then our eighth term is going to be, oops, I wrote that wrong. All right? A sub 4, not our eighth term, but our fourth term is going to equal 8. Now, with a sequence, many times we want to find out what is the nth term. All right, the nth term. The nth term is the last term in a sequence. So, in order to find this last term, we're actually looking for a term that has a variable in it. Well, terms that have variables in it, they are actually something familiar that you've probably said before. These are known as equations or formulas. And what we have here is we're looking for a formula or an equation that will represent this sequence. Okay? Now, when we say these formulas or definitions, okay, a bunch of different ways of saying this, is that we're going to use some things to help us figure this out. Okay? And to do that, we're going to think about some things. I'll come back to this example in a little bit. Because I like to think about sequences as functions. Because sequences and functions are very, very similar. Okay? Because functions, when we talk about functions or equations in Algebra 1, we talked about all these number patterns. All right? We're given a table, and we have to figure out an equation for those. We had this thing that was called a domain, inputs and outputs. We had a graph. We graphed these. We saw the infinite amount of points, and we connected the dots. And then we eventually began to call these equations functions. And we call them like f of x equals y. And the y always equal to like an equation. Equation in terms of x, correct? And we had that. So we had an equation in terms of x. Well, with sequences, we have something very similar. We also have all inputs and outputs. Except the domain for sequences is that we only can have, all right, non-negative integers including 0. So when we're talking about sequences, we cannot plug in all real numbers. We only can plug in non-negative integers, which would be like 1, 2, 3, 4, 5, like whole numbers. The other thing is that with a graph, we can also graph sequences, all right? It can also be graphed. But the thing is that instead of having connected points, we just have points. That's it. All right, that's it. The other thing is that instead of having f of x, we have a notation. All right, and this is called a sub unit n, all right, or a sub n. So it's very similar. So we have a sub n, which equals a term, all right, or the last term, I should say, which just generally is an equation, a function, in terms, in this case, in terms of n. Okay, in terms of n. So functions and sequences are very, very similar. They're very similar. And so what we're going to talk about is how to find, all right, the nth term of a sequence, all right, by thinking about functions. Think about functions. So let's go back to this other example that I just created. And what I have is an equation of 2, 4, 6, and 8. Okay, and this is an infinite sequence, so it keeps on going on. And you probably can notice that you guess that it's going to equal 10 is my next number, all right, and 12, and it keeps on going. And you realize that, okay, I'm writing all even numbers. At least that's what a lot of students will say. We're writing even numbers. Well, that doesn't help us out, okay? That doesn't help us out. Now, you can graph this, maybe to get us a better picture of it, by creating a set of points, okay? So we can figure out this number pattern because we're looking for a sub n, which is our equation, our last term. And to help us do that, I'm going to just create this set of points. So if I have a sub 1 equals 2, that means my output is 2, my input is 1. So I'm going to plot this just like I would normally do a normal everyday graph, but I just play 1 point. So this one would be 2 and 4. 2, 1, 2, 4, and we have that. We have 3 and 6, 3 and 4, 5, 6, and you may notice a little pattern. If I were to make this a function and kind of draw an imaginary line coming across here, all right, I'll just draw my line right there. You can see that this actually is a line, all right, and that's what my sequence is. Okay, its sequence appears to be linear. All right, they all have that same, have a similar slope and whatnot. So with that, because it looks like we have a linear pattern, well, what we can do is maybe create a linear equation. All right. So if we think about this, it appears that each one of these are going up by 2, so we're adding 2 each time. So in order to do the second term, I take the first term and I add 2 to it. All right. And then to find the third term, I take the second term and I'm going to add 2 to it. And then to find the third term, or sorry, the fourth term, I'll take the third term and add 2 to it. And I keep on doing that pattern. I'm just adding 2. This 2 that I'm adding seems to be a common difference. Okay, common difference. So what would be my equation? Well, it would be, well, if we put this as an equation form, a sub n, all right, appears to be, well, we take the previous term and add 2. All right, so it would be the previous term and add 2. All right. But that's not good enough because we want it in terms of just simply n and have an equation. Well, maybe it would be like 2 times n. 2 times n. Well, 2 times n, what we have here would be, well, let's just test it out. If I plug a 1 in here, all right, this is my input. All right, I plug a 1, I get 2. I'll plug a 2, I get 4, and I plug a 3, and I get 6. I plug a 4, I get 8. And if I plug an n in, I get 2n. So right here, this is my nth term. That's my nth term. This right here, and which is also known as an explicit definition. Okay, so this is what's known as an explicit. Oops. I need the extra I over there. All right, explicit definition. All right, or nth term. This right here, what I drew out, all right, is what would be known as another way to write this, but we would have to have an initial condition of saying 2. This is what's known as a recursive definition. Recursive definition. Recursive definition. A recursive definition, all right, and here's an example. Oops. Oh, no. Where am I going? Okay, here we go. Recursive definition, hang on one second. An explicit definition, or nth term, is what we use is when we create a formula, okay, is a formula. So that's an explicit definition. A recursive definition, okay, recursive definition that we have right here, recursive definitions are used to identify a pattern, all right, using previous terms or terms, okay. So when we have this over here, we'll look at this, okay, is that in our example, when we created or tried to define this sequence that we had right up here, okay, and we define this sequence in the nth term, all right, as using a formula, all right, what we just created was an explicit definition. When we create an equation that uses the previous term to identify it, so we use like a sub 1, a sub 2, a sub 3. So to find a sub n, I have to use the previous one, a sub n minus 1. all right, a sub n minus 1. So whatever the previous one is, because you notice I used 3, all right, instead of 4. All right, I used 2 instead of 3. I used 1 instead of 2. All right, and I added 2. That's what's known as a recursive. And then I have to define an additional condition. So that right there, a sub 1 equals 2. All right, so that was an introduction to what sequences are. We identified a sequence. Oops, sorry about that. We identified a sequence as a pattern of numbers. Okay, this pattern of numbers can be represented as a graph using points. We can also represent this pattern of numbers with an nth term, okay, an nth term, or identify the last term and create an equation that can define it. We can also, that's known as explicit definition, is also a recursive, all right, definition as well. In doing so, we identify that to help us identify and understand sequences better. They are very similar to functions. They have a domain, but only have integers, non-negative integers. They can be graphed, but there's only a set of points. And also, finally, we use a sub n, all right, a sub n, and not f of x, all right, use f of x, all right. But in any case, they both can be represented as equations, all right, and they both can represent numbers. All right, we're going to have some other tutorials and going through it how to find nth terms in this next series.